Hello everyone, welcome back to our channel. Let's discuss the principle of NMR spectroscopy. Before going to discuss about the principle, let's see some fundamental concept. Nature of nucleus. We all know that atom is composed of protons, electrons and neutrons. Protons and neutrons present at the center part of the atom commonly called as nucleus. The electrons are revolving around the nucleus in different parts according to the different theories. Right? So here we are talking about what? Nucleus. The nucleus is what? Positively charged heavy denser particle of an atom. Whatever the positive charge we are having, that is in what? Unipositive charge distribution is uniform in nature. Simply we can say that nucleus is composed by protons and neutrons. So the charge of proton is positive in nature, neutrons zero charge. That's why the charge of nucleus is what? Unipositive charge. Okay. Whenever we talk about NMR spectroscopy, we are discussing about the spinning particles or spinning nucleus. Only spinning nucleus can be identified by the NMR. The main aim is what? Behavior of the nucleus or not. So which kind of the nucleus we need? The nucleus should be spinning in nature. The spinning nuclei will be studied by NMR technique. So how can we identify spinning particle? See this one. In case of the carbon 12, we are having even number of protons and even number of neutrons. Because of this situation, what we are observing, no rotation. Already we know that electron is a spinning particle. Why? Because it can rotate around its own axis and rotate around the nucleus, always in continuous motion. That's why we are saying that it is a spinning particle. So in case of C12, rotations are not possible. That's why it is not a spinning particle. But in case of C13, the rotations are possible. That's why it is a spinning nucleus. It is very important question. Why C12 is inactive? Why are we studying C13 NMR spectra? Why not C12 NMR? Why? Because C12 is not a spinning particle. NMR deal with only spinning nucleus. C13 is the spinning nucleus. That's why we study C13 NMR spectra only. So in case of 1H1 also, we are observing the rotations. That's why we are going to study proton NMR spectra also. So here we are having some considerations. So every spinning particle generates what? Magnetic field or not? Right? Our nucleus is what? Charged particle or not? Here situation, any charged particle develops the magnetic field. So our nucleus is also charged particle. If rotations are possible, if spinning is possible, then that can also create a magnetic field or not. Generally, the strength of the magnetic field is calculated by using what? Magnetic moment. Spinning particle means what? Rotations are possible or not? So, any rotating particle is having angular moment or not? So, spinning particle means rotations possible. That's why we are having the component called as angular moment. Spinning particle is a charged particle. That's why develops the magnetic field. That's why we are going to have magnetic moment also. So two quantities we are having, angular moment and magnetic moment. Okay. So this is the relation. The relation between the angular moment and magnetic moment. By using these equations, we can calculate. Here I is the what? Spin quantum number of the nucleus. K is the constant. From that we are getting what? Gamma, gyromagnetic ratio. It is the characteristic of each and every nucleus. This value is different and unique for each and every nucleus. That's why we can get different informations from the different nucleus. So this is the relation mu equal to gamma into I. Magnetic moment, angular moment, gyromagnetic ratio. Okay, here we are using the word called as what? Spin quantum number of the nucleus. How can we identify whether the given nucleus is spinning in nature or not? Why? Because NMR is saying that NMR will identify only spinning particle. So in order to have the information, we should know the given particle is spinning in nature or not. So how should we know? That can be known by using spin quantum number. See this one. This is the criteria. If the nucleus is having even number of protons and even number of neutrons, the spin quantum number value is 0. It means there is no spinning, no magnetic moment, no angular moment. So not used in NMR. C612, O816 are the examples. Suppose if the nucleus is having odd number of protons, odd number of neutrons, the I value is going to be integer. Spinnings are possible. Some U value will be there. Some I value will be there. So can be used in NMR. Suppose the nucleus is having odd number of protons, even number of neutrons, even number of protons or odd number of neutrons. I value will be the non-integer. So some U value will be there, some I value will be there. So it can be used in NMR. Simply, whenever the nucleus is having some value, so blindly we can say that nucleus is spinning in nature. That is the spinning particle. If you have I value, that can be identified by the NMR spectra. Okay, so here is the table. From this table, you will get complete data with examples. Even, this spin quantum number 0. These are the examples. Sometimes people will ask you which are the nucleus cannot be studied by NMR. You can give the information. Okay. Mainly these two, number of protons and the number of neutrons. Even, 0, even odd, odd even, non-integer value, odd integer value. These are the examples. So you should remember the I value of each nucleus. F19 I value 1 by 2, N15 1 by 2, P31 1 by 2, 13C 1 by 2. In this way you need to remember the I values. Deuterium I equal to 1, 7 and 14 I equal to 1. Okay. Here is a condition, see this. Whenever the I value is greater than 1 by 2, the positive charge distribution is not uniform in nature. The type of nucleus is commonly called as quadrupole nucleus. If we have more than one nucleus, commonly called as nuclei. It means if you study the NMR spectra of deuterium and N14, the I value is more than 1 by 2 or not. That's why we are going to study by using the terminology called as a quadrupole nuclei. Okay, so these are the some of the basic things which we need to understand before starting the principle of NMR. Okay, so let's start principle of NMR. Already we know that we are having how many approaches? Two approaches. First one is classical approach and second one is quantum approach. Quantum approach generally deals with the energy levels. Comparing with the classical approach, quantum approach is very 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 important. Okay, so let's discuss the quantum approach. For that purpose, what we are doing, we are taking one example, that is ethyl chloride. Okay, assume that, before the assumption, how many non-equivalent sets of protons are there in this molecule? In this molecule, two sets are not. One is this one, second one is this one. Why? Because the influence of chlorine on both the carbons are different or not. That's why we are going to get two different sets of protons. For example, for suppose, assume that chlorine is not affecting both the carbons. What is the meaning? All the protons are having same environment or not, right? These are commonly called as five protons are independent in nature. No effect of the chlorine. Chlorine is not influencing the five carbons. Okay. So five protons are free in nature. That's why free in nature means what? Their spinning is in the random nature. All the five protons are randomly rotating in their axis with respect to their convenience. Okay, for our convenience, what we are doing, we are representing each and every nucleus with the arrow. Why? Because the spinning particle is having what? Magnetic moment or not? Magnetic moment means it is having direction or not. That's why we are using the symbol. The people will ask you in the interviews, why are you using these kind of arrows for the representation of spinning particle? You should say, sir, spinning particles are the magnetic in nature. They develop the magnetic field. So magnetic field means they are having the direction. That's why we need to represent in this way, right? Suppose, right, we have this molecule. So according to general criteria, what we are observing, this is a set of proton, this one is b set of proton. Suppose if chlorine is not influences, so all the five protons are free from the influence of the chlorine. That's why all are independent in nature. So independent means they can rotate in any direction. That's why that is commonly called as what? Random in nature. Okay, so whenever we place this kind of situation in an external magnetic field, what will happen? Let's see. Before seeing that, see this. Quantum approach deals with the generation of nuclear energy levels. Why? Because NMR technique deals with the nucleus and it's a generation of energy level, commonly called as what? Nuclear energy level generation. Okay, so now we are saying that if any kind of nucleus is not influenced by any third partner, see in the case of chlorine we are assuming that chlorine is not influencing these. This is one consideration. Second one is that electron density, right? If the particle is not associated with any electron density, no electron clouding, in such cases the independent nuclei are commonly called as, what is the name? Naked nuclei, bare nuclei, or isolated nuclei. This terminology is very very important. We have a spinning particle. The spinning particle is not influenced by any electron cloud or not influenced by any other external nucleus. Then the nucleus is said to be naked nucleus, bare nucleus, or isolated nucleus. If you have group of nucleus, commonly called as nuclei. In such kind of nuclei, isolated nuclei taken under the normal condition without external magnetic field, the spin orientations are random in nature. See this one, how these are rotating. There is no influence of any other person or any other field or any electron density. All are free. That's why they can randomly move. Okay, so these protons are commonly called as what? Isolated nucleus, naked nucleus, or bare nucleus. Okay, so all the nuclei which are having the same energy, if there is no influence, all are having the same energy, that is commonly called as what? Degeneracy. Degeneracy means all the independent nuclei are having the same energy. Whenever these kind of nuclei placed in the external magnetic field, what will happen? The degeneracy get eliminated. Suppose assume that we have a classroom. In the classroom, for example, 30 students are there. Okay. Suppose teacher is not there in the class. What will happen? All the students will randomly sit in the tables. Right? Suppose assume that suddenly teacher entered the room. What will happen? All the students will not be aligned with the teacher at that moment. Some of the students are aligned with the teacher, some of the students are not aligned with the teacher. At that moment, if the teacher suddenly enters into the classroom, similar kind of situation, assume that in a classroom you have some nuclei. The nuclei are randomly moving. Okay, from the backside, suddenly we are sending teacher in the form of an magnetic field. So what will happen? Some nuclei align with the magnetic field, some nuclei opposes the magnetic field. See this one. Nuclei takes only two possible spin orientations. Little excess nuclei orients parallel to the direction of external magnetic field. Little less number of nuclei anti-parallel or opposed to the direction of the external magnetic field. So nuclei which are parallel arranged having the lower energy, which are having the anti-parallel having the higher energy, according to the z-axis convention. Generally we are using z-axis convention in this one. See this one. This is the initial situation, right? We have 5 nuclei in this example. So all the 5 nuclei is not influenced by the chlorine or any external field. So all are independent in nature, randomly moving. Now what we are doing? We are going to place these 5 in the external magnetic field. Once you place all these in the external magnetic field, what happens? Maximum nuclei will align with the magnetic field. Align means with the same direction of the external magnetic field. See this one. Magnetic field direction and these 3 protons direction is same. So maximum number of nuclei will be aligned with the field and minimum number of nuclei will be opposes the external magnetic field. So if you have a hypothetical line, these lines are commonly called as nuclear energy levels. This is commonly called as what? Generation of nuclear energy levels. It's very, very important. Quantum approach deals with the generation of nuclear energy levels. So how the energy levels are generating in this way? What is the condition? We have some nuclei. There is no influence uh, of these nuclei by the other external field or other electron density. Under that condition, these nuclei are commonly called as isolated nuclei, bare nuclei, or naked nuclei. These nucleus, once placed in the external magnetic field, what happens? Some of the nucleus will take the parallel direction with the external magnetic field, some will take the anti-parallel direction with the external magnetic field, thereby the generation of energy levels possible. These energy levels are commonly called as nuclear energy levels. So now we are under this condition. See this one. All the five nuclei is placed in the external magnetic field. So these are present inside the magnetic field. Okay, this is h naught. h naught. So in presence of the external magnetic field, we are having two energy levels. So under this condition, what we are doing, we are sending radio frequency radiation. We have the electromagnetic spectrum, right? Electromagnetic spectrum is the combination of different kinds of the electromagnetic radiations based on their energy or their frequency or their what we call wavelength. So we have one portion of the electromagnetic spectrum having radio waves. Radio waves are generally used in the NMR, commonly called as radio frequency radiation. So once this kind of system is irradiated with radio frequency radiation, what happens? The nucleus which is present in the lower energy level will absorb some amount of energy and shifted towards the higher energy level. Thereby, absorption of electromagnetic radiation takes place. The absorbed energy is converted into the signal, that is NMR signal. So this is called quantum approach. I think you understand the generation of nuclear energy levels and everything. Okay, see this one. Nuclear which are under the influence of external magnetic field, once irradiated with the radio frequency radiation under resonance condition, nuclei which are with low energy will take energy from the radio frequency radiation, undergoes spin opposition, occupies beta levels, also called as nuclear upward transition or flipping. The absorbed energy by nuclear from the radio frequency radiation transformed into proper NMR signal. Here we have taken proton, right? That's why we have generated two energy levels, right? The energy levels are generated due to the presence of water, magnetic field or not. That's why we are representing Mi. Okay, magnetic orientations, spin magnetic orientations. So here the rule is always delta M equal to plus or minus 1. Okay, so we have two lines, right? In this way, always this is M1 M2. So M2 minus M1 is always plus or minus 1. Delta M, the change is always plus or minus 1. Suppose if you take different nuclei, how can we identify the number of orientation is nothing but one energy level. If two orientations are there, two energy levels will be generated. If three orientations are there, three energy levels will be generated. That is based on the what? Spin quantum number of the nucleus. So this is the formula everyone should remember. The number of possible spin orientations or the number of possible generation of the energy levels represented by 2i plus 1. See, in case of hydrogen, I value is 1 by 2. That's why the magnetic spin orientations are 2. So we will get 2 energy levels. In case of deuterium, I equal to 1. So you will get 3 energy levels. Now, very important condition that is commonly called as a resonance condition. See, one thing is very important. What we are doing here, under this condition we are supplying radio frequency radiation or not, right? We are saying that once the system is irradiated with radio frequency radiation, Some nucleus will absorb the radio frequency radiation and move towards the higher level, thereby absorption of energy takes place. So when will the absorption of energy takes place? The absorption of energy takes place only if the system satisfies the resonance condition. See the name, nuclear magnetic resonance. We are talking about the nucleus. Nucleus must be what? Spinning particle. Spinning particle is always what? Magnetic in nature or not? That's why nuclear must be magnetic in nature and should follow what? Resonance condition. Now see what is the resonance condition. The resonance condition is that whatever the energy you are supplying to the system, that energy must be equal to the energy gap between these two energy levels. If the energy difference between the energy levels matches with the energy of radio frequency radiation, then only absorption of radio frequency radiation takes place. That is commonly called as resonance condition. Okay, every transition doesn't lead to the absorption of energy. Only those transitions leads to the absorption of energy where the energy gap between the energy levels should be equal to the energy of radio frequency rate. It's very very important. In every interview people will ask you what is the resonance condition according to the quantum approach. What is the resonance condition according to quantum approach? This one. Matching of energy gap of the nuclear energy levels and the energy of radio frequency radiation said to be resonant. Simply, how can we represent? Energy of the radio frequency radiation must be equal to the delta E. How can we get the delta E? Higher level energy minus lower level energy. Okay? So, in this way, we can get the NMR signal. Okay? This is the general description. Lower energy level, higher energy level in case of hydrogen. Plus 1 by 2, one level, minus 1 by 2, another level. This is the delta E. Okay. Here see this one. Nuclear energy levels gap very small compared to the rotational, vibrational, electronic levels. Therefore, under given set of conditions, less number of nuclei also taking higher energy level. Already we know that if you take a system, there we are observing what? Rotational levels, rotational spectroscopy, vibrational level, vibrational spectroscopy, electronic level, electronic spectroscopy. Electronic spectroscopy is commonly called as what? UV visible spectroscopy. Vibrational spectroscopy is what? IR spectroscopy, rotational spectroscopy. Rotational spectroscopy is going to give the information about the bond lengths and bond angles. They will consider the rotational levels only. So now we are talking about what? Nuclear energy levels. What the people are saying, the energy gap between these nuclear energy levels is always smaller than rotational, vibrational and electronic levels. That's why what happens sometimes, some nuclei can also jump into the higher energy levels. So what the people are saying, if you increase the strength of the external magnetic field, automatically what happens? The energy gap will be increases. The another thing is, if we increase the energy gap, the number of particle at alpha level will be increases and the number of particles at beta level will be. This is the common sense here. If the distance increases, what will happen? The nucleus needs more energy to jump into the higher energy level or not. This is the simple thing, right? So according to quantum approach, this is the formula we have. Delta E, the difference between the energy levels. equal to h into gamma into h naught by 2 pi. H is the Planck constant, gamma is gyromagnetic ratio, already we discussed. Gyromagnetic ratio is the unique property of each and every nucleus. If you talk about hydrogen, hydrogen has the fixed gamma value. H naught is what? Strength of the external magnetic field. Pi is the constant, H is the constant, 2 is the constant. Already we know that according to the Planck quantum theory, delta E equal to h nu. So if you substitute this value here, what happens? H and H both will be cancelled. Then the frequency equal to gamma into h naught by 2 pi. Here we are using radio frequency radiation or not? The radio frequency radiation can be identified by using lambda, by using frequency, right? So if you know the frequency, indirectly what we are knowing, energy or not. So generally whenever you talk about the wavelength or frequency, the indirect meaning is that we are talking about the energy of the system. If you know the wavelength, you can calculate energy. If you know the frequency, we can calculate energy. That's why whenever you use these kind of terminologies, now indirectly in your mind you should think that I'm talking about energy of the system. So frequency is equal to gamma into h naught by 2 pi. See, gamma is constant, 2 is constant, pi is constant. So how can we write? Gamma is directly proportional to h naught. Otherwise, if you take this one, h constant, gamma constant, 2 constant, pi constant. That's why delta is directly proportional to what? H naught. This is very, very important point. If you want to increase the energy gap between the energy levels, what should we do? We need to increase the strength of the external magnetic field. If you want to increase the frequency, then also you can do increasing the strength of the external magnetic field. It means if you want to study NMR spectroscopy, you should aware about the strength of the external magnetic field and its influence. Every time we will use strength of the external magnetic field. Okay, so keep remember these two things: formation of nuclear energy levels and the effect of h naught on the energy levels, energy gap and the frequency. So these are the some values. By increasing the strength of the external magnetic field, what is happening? The frequency is going to be increased. These are the fixed values everyone should remember. Nowadays the people are saying in the laboratory we are having 500 megahertz NMR spectrometer. It means that what? In that magnetic spectrometer, the people are using the magnetic field strength that is 11.75. Okay, now let's discuss population of nuclei at the energy level. We all know that from the UZ, we are discussing Boltzmann distribution of the population of different kinds of the particles. The similar situation we are applying here only. The same formula we are applying here. N alpha by n beta equal to e power delta E by kt. If you reverse this, we can put minus here. Alpha is population of nuclei at n alpha is population of nuclei at lower level, n beta is population of nuclei at higher level. Okay, so this is one example we have. At 17 degrees centigrade it is like this. Increasing the field strength, what happens? Energy gap increases, thereby what happens? Increased field strength, increased population at alpha level. Common sense. Even at a higher temperature, the population difference is too small, only little excess of nuclei. Increasing population at alpha level, more number of nuclei at alpha level, more upward transitions, more amount of energy absorption, increasing in the intensity of. This is the point which we need to remember, right? If you have more number of nucleus at the lower level, what happens? More number of absorptions takes place, thereby whatever the signal we are having, that signal intensity is going to be increased. Okay, The another thing, relaxation. It's very very important and very very simple one. See, by supplying the radio frequency radiation, what is happening? The particle is jumping from the lower energy level to higher energy levels. Already we know that in photochemistry we have studied the particles are highly unstable at the excited state. This is a kind of excited state or not? So in the excited state, what happens? The particles are not stable. That's why what happens? After some times, the particles will return back to the original level. That is commonly called as what? Relaxation. While irradiating the sample with radio frequency radiation, not only upward transition, even downward transition simultaneously takes place with the emission of the radiation. See the definition. Returning of nuclei from beta level to alpha level by releasing excess energy commonly called as relaxation of nuclei. Be relaxed, have a charminor. People will say, na? Right? So here the relaxation is what? Returning of the nuclei from the higher nuclear level to the lower nuclear level by releasing the excess of energy. Here we have two types of relaxation: spin relaxation and spin lattice relaxation. Two types of relaxation: spin relaxation and spin lattice relaxation. What exactly? Spin relax. In relaxation, what is happening? Simply particle is coming from the higher energy level to lower energy level. Here what is happening? Some excess amount of energy is released. Emission of radiation is takes place, right? Whatever the energy is coming, that is responsible for spin and spin lattice relaxation. Spin relaxation means whatever the excess energy coming when the nucleus is coming from the higher energy level to lower energy level, if the excess energy is used for the excitation of the another nuclei, then the relaxation phenomena is commonly called as spin relaxation. Okay, that is spin. In case of spin lattice relaxation, what happens? Whatever the excess amount of energy is coming, that energy is going to the lattice, that energy is going towards the system lattice, then that is commonly called as spin lattice relaxation. Okay, so relaxation, spin relaxation and spin lattice relaxation. This is also one important point: saturation of nuclei. So even we also saturated when we teach now. If we teach more than 2 hours, we will get some point that is commonly called as what? Saturated point. So in this case, saturation means what? Generally, in case of proton, we are having two levels or not. If the number of nucleus present at a higher level and lower level become equal, then the situation is commonly called as saturation. See this one. While recording the NMR sample, sometimes nuclear energy levels population becomes same. The number of nuclei at the alpha level and the number of nuclei at the beta level will be same. Then the situation is called as saturation of nuclei. If the saturation phenomena takes place, there is no appearance of signal. This is not good condition for the NMR. So when will we get the signal? High number of particle at the lower level, low number of particle at the higher level. Thereby what happens? There is a possibility for the shifting of proton from the lower level to higher level. Then we can get the signal under the resonance conditions. If the number of particles are same, there is no chance for the transition. No? If you have unsaturation, then only something will happen. If you are saturated, nothing will happen. So similar situation here also. If the number of particles are same at the lower level and the upper level, there is no chance for the absorption of the radiation. There is no chance for the shifting of nucleus from the lower level to higher level. That's why there is no chance for the NMR signal. Okay, so while recording the NMR signal, we must prevent saturation phenomena. Okay, so this is about your quantum approach. Very, very, very important approach. Okay, now come to the next and very, 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 very simple approach, that is classical approach. The name itself indicates classical, simple. The classical approach deals with what? Spinning particle only. See, the basic criteria is same in both the approaches, right? Explanation is different. Classical approach is considering behavior of the gyroscope or the behavior of the top. Generally, the physics students aware with the gyroscope, the chemistry and all kind of students aware with the top. बचपन में हम सब लोगों ने खेला था ना टॉप के साथ. Assume, okay, how you have played with the top. All should can remember how the top is going to rotate whenever it is in the rotation. So when you start the classical approach, the top should be in your mind. बचपन में आप लोगों ने जो टॉप के साथ खेला था वो सिचुएशन आपका माइंड पे आना चाहिए. If you have that situation in your mind, you can easily understand the classical approach. Okay, so gyroscope is a spinning body. See, NMR deals with spinning particles only. So we will have the phenomena of spinning. Okay, let's take the example. NMR technique is mainly using magnetic field or not. That's why whatever the sample you are having, that is going to be placed in the magnetic field only. So in classical approach, what we are identifying, we have a top. If you observe the rotations, the top rotations, that is always elliptical in nature. बचपन में आप लोगों ने देखा है, when you use the top, that can always rotate like this. This is situation na. So always this rotation is elliptical in nature. Okay, so similarly assume that your hydrogen is a spinning particle, your hydrogen is a top. Okay, now what I am doing, the hydrogen is going to place it in the external magnetic field. See this, hydrogen is the spinning particle, the spinning particle is placed in the external magnetic field. What happens, the spinning particle takes the parallel orientation with the external magnetic field and rotate in the elliptical path like a top. This is the imaginary axis which we are assuming. This is strength of the external magnetic field. So the situation is, we have a nucleus. The nucleus is placed in the external magnetic field. Then the nucleus take parallel direction. This is the nucleus is going to take the parallel direction with the external magnetic field and rotated by taking the elliptical path around the external magnetic field. This phenomena is commonly called as precision. What is the name? Precision phenomena we are observing. Precision means what? Whenever a spinning particle is placed in the external magnetic field, the spinning particle will take the parallel orientation with the direction of external magnetic field and continue its rotation in an elliptical pathway. That phenomena is commonly called as precision. The phenomena was given by Sir Joseph Larmor. Okay, so simply the spinning particle is rotating around the nucleus, right? So if it is rotating around the nucleus means we have the rotation number or not. Suppose if you fix the time, 1 minute 10 rotations, 2 minute 20 rotations, 3 minute 30 rotations. It means that what? The nucleus is going to be rotated around the direction of the external magnetic field with respect to the time, right? That number is commonly called as precisional frequency. What is the name? Precisional frequency. Precisional frequency means the number of rotations performed by the spinning particle around the nucleus in a given time. Suppose I have given 1 minute time. Within 1 minute time, my nucleus rotated around the external magnetic field with 100 rotations. So 100 is the Fresnel frequency. If the rotations are 200, that is the Fresnel frequency. If the rotations are 500, that is the Fresnel frequency. Simply the number. Okay. The precisional frequency is also called as Larmor precisional frequency. Why? Because Joseph Larmor has given this situation. Okay. So under this condition, what we are doing, we are supplying the radio frequency radiation. Okay. Initially, what we have done, we have taken only one spinning particle, right? Spinning particle is independent in nature. Independent particles are commonly called as what? Naked nucleus, bare nucleus, or what is the third one? Isolated nucleus. Right? So now what we are observing here, precision phenomena is taking place. Continuously my nucleus is rotating around the external magnetic field. Now what I am doing, I am sending the radio frequency radiation. If I continuously send the radio frequency radiation, what happens at one time? This nucleus will take the opposite direction. Right now, what happens? The nucleus is parallel to the external magnetic field or not? After some time, what happens? My nucleus will take anti-parallel direction to the external magnetic field and continue its rotation in the elliptical path. And continue its rotation in the elliptical path. If the situation arises, that means my nucleus absorbed some amount of the radiation from the radio wave. This is commonly called as classical approach. In case of one nucleus, this is the situation. If you have more number of nucleus, that can be represented like this. In the textbooks, people are representing like this. More number of nucleus means more arrows. Like this, we can represent. So, this is the situation. More number of nucleus. Okay. So, once again see, any spinning particle if rotates around the direction of external magnetic field in a elliptical path, the situation is commonly called as precision. Spinning nucleus whenever placed in the external magnetic field takes the parallel orientation with the direction of the external magnetic field with some angle alpha. That angle is commonly called as a tip angle. Then undergo rotations about the direction of external magnetic field by taking an elliptical path, phenomena called as nuclear precision. Our nucleus is taking, no? Right? Nuclear precision. So the number of rotations performed by the spinning particle about the direction of the external magnetic field in a given time is commonly called as what? Precisional. It is very, very important. Each and every student should by heart, should remember the precisional frequency. What is precisional frequency? Precessional frequency is the number of rotations performed by the spinning particle around the external magnetic field in a given time. Within the particular time, how many rotations are performed by your nucleus? That number is commonly called as precessional frequency. This is also called as what? Larmor precessional frequency, because introduced by Sir Joseph Larmor. So now what happened? Once the precessioning nucleus is aligned with the external magnetic field under the resonance condition. Now see, here also we should have a resonance condition. I explained that we have the nucleus continuously rotating and absorbing the radiation. At one time what happens? It will take the anti-parallel direction and continue its precession. So when will it take the anti-parallel direction? When? If the nucleus satisfy the resonance condition. In quantum approach, we know the resonance condition. What is the resonance condition? The energy of the radio frequency radiation must be equal to the energy difference between the energy levels. So here what is the condition? So when will the opposition of the nuclei takes place? The resonance condition is that matching of the frequency of radio frequency radiation and precessional frequency of the nucleus is commonly called as resonance. It's very simple. Radio frequency radiation having the frequency, our nucleus is continuously rotating, that's why it is having precessional frequency. Whenever the precessional frequency matches to the frequency of your radio wave, then what happens? Absorption of the energy takes place. That's why the nucleus takes the opposite direction with respect to the external magnetic field. Okay, so the equation is gamma L equal to gamma into h naught into the, this is gyromagnetic ratio constant, but this one is frequency. So what is the relation? Precessional frequency is directly proportional to the h naught. So three conditions we should remember. What is the first condition? Delta E is directly proportional to h naught. What is the second condition? General frequency is related to h naught. Precessional frequency is directly proportional to h naught. So every student should remember these three conditions. Relation between energy, difference between the energy levels and the magnetic field, frequency and the magnetic field, precessional frequency in the magnetic field. Okay, so these are some of the values with respect to the magnetic field strength. So what are the factors which influences the precessional frequency? See, these are the factors: nature of nucleus, strength of external magnetic field, magnetic momentum of the nucleus, gy- gyromagnetic ratio, electron crowd around the nucleus. Let's see one by one. So different elements nuclei will have different gamma L at the given field strength, so different Fresnel frequencies. If you see, gamma L equal to gamma into h naught by 2 pi. So this gyromagnetic ratio is different for every nucleus or not. That's why Fresnel frequency should be different. Okay, the second thing, h naught, external magnetic field, just now discussed. Fresnel frequency is directly proportional to the strength of the external magnetic field. It means if you increase the strength of the external magnetic field, what happens? It can increases the Fresnel frequency. The Fresnel frequency is directly proportional to the magnetic moment. Magnetic moment increases means Fresnel frequency is going to be increases. C13 magnetic moment is approximately 4 times lesser than the proton magnetic moment. That's why the precisional frequency of the C13 is 4 times lesser than the proton. Very, very, very important sentence. Why the precisional frequency of proton is higher than C13? Because the magnetic moment value of the C13 is lower. That's why the precisional frequency of the C13 is 4 times lower than the proton. Very, very important. Okay. So electron cloud around the nucleus. See this one. This is the situation. We have discussed both the principles, quantum approach and classical approach with respect to the isolated nucleus. It means that what? There is no influence of any other external magnetic field. There is no association of the electron cloud. Suppose if the nucleus is surrounded by electron cloud, what will happen? The precisional frequency will be increased or the precisional frequency will be decreased. This we'll discuss in the next class. Okay. So before discussion, let's think. If we have some electron density around the nucleus, the precisional frequency will be increased or decreased. If you know the answer, then please give some comment. Okay. So we will meet in the next video with the another topic in the NMR spectroscopy.